Alright, so it's a long way behind me, but the sun is just rising over the ocean, and today we're going to learn about the difference between heat and temperature. Temperature, as you know, is the average kinetic energy of molecules, where heat is the transfer of that energy from a hot thing to a cold thing. The sun, who's just coming up, is a ridiculously hot thing, and our planet without the sun would be a ridiculously cold thing. So, the sun transfers its heat to us via lots of different parts of the electromagnetic spectrum, and thankfully we get that heat. Otherwise, life would not exist on Earth. So, enjoy the sunrise.
Alright, so today we're going to talk about KMT, which is the kinetic molecular theory, and essentially the lab we did in class with the PhET simulation, with looking at the gases and how pressure and temperature and volume are all affected. Scientists started seeing these relationships and wanted to kind of come up with a set of rules that said, if this is true, this is true, this is true, this is why particles behave the way they do. So, the kinetic molecular theory is what they came up with back in probably the 1700s to describe gas behavior. So kinetic molecular theory, and it is a theory, it's not a scientific law, so it's a theory still, but there's basically 5 ideas. The first idea simply is that gas particles are in constant, rapid, random motion. Alright? So constant, rapid, random motion. Alright, which kind of means if we could see them, you know, obviously they're too small for us to see, but they are just going everywhere in the room, hitting walls, hitting ceilings, hitting us. Constant, rapid, random motion. Alright? And that's what kinetic means in kinetic molecular theory. Kinetic has to do with motion. Alright, so that is the first idea, and that's true of gases. The second idea is that temperature, we're just going to call this big T, alright, is proportional. That's what this little symbol right here means. Temperature is proportional to the kinetic energy of our molecules. Alright? So you might need to spell that out in your notes, but temperature, capital T, is proportional. Okay, so instead of being equal, we don't have an equal sign, but it's proportional to the kinetic energy. And simply what that means is kinetic energy is energy of motion. Yet again, just kinetic molecular theory again. So if the molecules are moving really quickly, the temperature is high. Or we would say it feels hot. If the molecules are moving slowly, we would say that feels cold. Alright? So all that is saying, if we have steam, which is water is a gas, its molecules have a bunch of energy. They're moving really, really, really quickly. If we put that steam in a regular room, what happens? Those molecules lose the heat, because in order to get steam, you probably have it on a stove boiling. But those molecules lose energy, and they condense into liquid. Alright? And eventually we can cool those even further. We put it in a freezer, and now they are a solid. Okay? So liquid is still moving, there's still motion there, and solid, they're kind of locked in place. So temperature is proportional to kinetic energy. Alright, the next thing is gas particles. The actual particles themselves, we can see them, are neither attracted nor repelled by each other. Neither attracted nor repelled by each other. By each other. Alright. So again, this is just saying, if our gas molecules they're moving so fast, and they're so small, they hit each other, they kind of just ricochet off. Hit the walls, they ricochet off. They're moving so fast, if you think of 2 magnets, okay? If you've played with magnets before. If you have them on a table and you fling them past each other real quickly, they don't have time to be attracted to each other because they're moving so quick. What happens if you pass them more slowly? They're going to attract and be attracted to each other, or if you have the opposite ends, they repel each other. But if they're moving fast enough, there is no attraction or repulsion. Okay? Number 4 is going to be gas particles have perfect elastic collisions. Okay, so when they bounce, there's no energy lost. So we might just say elastic collisions. And there's no loss of energy. And then our last one is volume is insignificant. Alright, what this has to do with is if we have a container, I don't have a container, but if I had a Tupperware container that has a certain amount of gas in it, it has a certain amount of volume, it takes up a certain amount of space. Well, if we were to magnify down and look at those gas molecules that are in my container, their size is so small compared to the space they're in that we can say their volume is negligible, and we can treat them as what we call point masses. So all of their mass is just in a teeny tiny point, and we just say all the mass is there because their volume is small, it's insignificant. Alright, so these are basically true, except for a couple of them. Alright, number 3 is false, and number 5 is false. Okay, there are in fact attractions and repulsions by molecules. Gases not so much, but certainly by liquids and certainly by solids. Alright? And the next thing is volume ends up being significant if our volume is really small or our pressure is really high. So way down below the Earth's surface when the pressure is really high, when we have rock and rock and rock, or maybe down in an ocean where you have water and water compressing, when the pressure is high or the volume is low, even though the volume of our gas is so small, if we have a really small volume, then that volume becomes more significant. Alright, so essentially what we're going to say is kinetic molecular theory is true for ideal gases. Getting a little bit ahead of ourselves now, but KMT is true for ideal gases. Ideal gases, we're going to say equal KMT is true. Alright, and for the most part in the world we live on, ideal gases are going to be real gases. Really, ideal gases don't exist. We have real gases, but where our pressures and volumes are on Earth, ideal gases become real gases.